And the final summary slide or video in this topic 11 of higher level diploma program physics is on capacitance, which is a measure of store of charge. Capacitance, big C, has a unit of farad, big F, and is defined as charge per unit potential difference, where Q is the charge on one of the plates. So we'll be talking only about parallel plate capacitors. We have two plates which are parallel to each other and have a surface area A and a distance between the plates of little d. And from the geometry of the capacitor, the capacitance of this parallel plate capacitor is equal to epsilon, which is a measure of the dielectric, times by the cross-sectional area of one of the plates, divided by the distance between the plates. So if the area on the plates increases, the capacitance increases, but if the distance between the plates decreases, if the distance between the plates increases, then the capacitance decreases. The circuit symbol, by the way, is this. It's two parallel lines. Make sure that you make the lines parallel and not unequal, because then it would look more like a cell. So first of all, what's a dielectric? Well, a dielectric is an insulating material placed between the plates, and the effect on their dielectric is always to increase capacitance. And there's two ways of reasoning yourself to this. One is when we have constant charge stored on the plates. In that case, when the dielectric is placed in between the plates, the material of the dielectric gets polarized, creating its own opposing electric field. So in this case, with constant charge, the net electric field decreases. Therefore, since electric field is proportional to potential difference, the potential decreases, and since capacitance is inversely proportional to potential difference, if potential difference decreases, capacitance will increase. In the second picture, we have a constant potential difference, so more charge can be pulled off, if you like. When the dielectric is put between the plates, again it gets polarized and creates an opposing electric field, so more charge is pulled off the cell in order to increase the net electric field, and therefore, since charge has increased, since capacitance is proportional to charge on the plate, then capacitance also increases. Now, what happens if we combine capacitances? If we combine capacitors in series, we have to do 1 divided by the total capacitance equals 1 divided by the capacitance on the first capacitor plus 1 divided by the capacitance on the second capacitor. This is from the fact that we have the same amount of charge stored on capacitor 1 as capacitor 2. However, when we connect capacitors in parallel, because the charge is split at the junction here, we have the same potential but different charges on the plates. We combine capacitors in this way. The total capacitance of two capacitors in parallel is just C1 plus C2. So that we use if you like, the inverse relationships when we combine resistors in series and parallel. You also have to know that the energy stored in a capacitor is the same as the area under a potential charge graph. If we have a potential charge graph, then the gradient is the one upon the capacitance, which is good to know. And through geometry reasons, this is just a triangle. The area under is the stored energy, and that's equal to 1/2 times capacitance C times potential difference squared, which is equivalent to charge squared divided by twice the capacitance. Now we can connect up something called an RC circuit, where we have a capacitor and a resistor connected in series. If we had the switch connected to this way, then the circuit would be charging. However, when we flick the switch onto this side, the circuit would discharge. So here are the potential and current graphs when it's charging. Potential would gradually increase asymptotically to the same value as the potential on the cell, whereas current would decrease exponentially. However, when we discharge the circuit, both potential and current decay exponentially, and there are a number of equations for the discharge circuit which you are given in the data booklet, and you would expect to be able to solve. And as an example, the potential equals potential V at any time is V0, the peak value, or the initial value of the potential at time equals 0, times e to the power negative t for time divided by tau, where this tau constant is the resistance times the capacitance. So if we were to increase either the resistance or the capacitance, then that would mean we would have a longer discharge time. It would take longer to discharge the capacitance. What could be interesting to note is that the same exponential decay behavior is seen both in the decay of the potential, the current, and the charge. But the value for the initial charge is the initial potential divided by tau, which is not given in the data booklet. Lastly, what's the effect of a capacitor on the diode bridge, which, remember from a previous video, the diode bridge is used to convert alternating current to direct current. If we were to connect a capacitor in parallel with the resistor in the diode bridge, then as opposed to not having a capacitor, then the red curve shows the effect of the diode bridge with a capacitor in parallel. You see that the voltage time graph is much smoother. So the effect of the capacitor on the diode bridge is to smooth out the curve.